This is 8.1, key features of a quadratic function. So we're going to start talking about bigger functions and graphing them. In the next two chapters, we're going to be dealing with quadratic functions. And the beginning part of it is right here. So f of x equals x squared. And this is called the quadratic parent function. And you're like, well, why is it called a parent function? Well, much like parents have, they have offspring, and, the offspring, they have similar traits to it. They might have similar eyes or hair or height or, whatever it is, and they have similar traits to it, but it all stems from the parent. So here we have f of x equals x squared, and so I'm going to talk about functions that might look like f of x equals 2x squared. So the original function is x squared, so what does the 2 do to the function? But the parent function is this, and so how does this, the offspring, this is like the offspring of the function, and so how does that relate to the parent function? Or I might give you f of x equals negative 1/2 x squared. How does it relate to the parent function? Or f of x equals 3x squared minus 9. But again, the parent function started with this, but notice it got multiplied by 3, and then 9 got subtracted from it. So again, the parent function is still there. It literally starts off at x squared. That's like the genetics of it. And then the offspring of it, again, got multiplied by 3, and then 9 got subtracted from it. So again, it's going to get more and more involved. So like, x squared, it might be x squared plus x minus 2. And so again, but the parent function is still there, x squared, and then how does the offspring, it's not really called an offspring, but this other function, how is it related to the parent function? And so that's what we're going to talk about, dealing with the key features of it. So let's back it up and deal with just f of x equals x squared. So if we wanted to graph this, we would make an xy chart, and we would literally plug in, this is your, remember, this is your same as your y. So this is your input, and this is your output, your domain and your range. So again, this is your input, and you can put any numbers. You don't have to put these 5 numbers in. You can put any number in whatsoever. It does not make a difference. You can put negative 37, positive 19.9. I mean, you can put any number in for the thing. But normally we stay with these 5 numbers because they're pretty basic. So if I put each of these numbers in, so let's start at negative 2. So negative 2 squared means negative 2 times negative 2. I'm going to get 4. So if I graph negative 2, 4, it would be right here. Put negative 1 in, and again, I'm putting it right here. So negative 1 squared is positive 1. So negative 1, 1. Put 0, 0 squared is going to give you 0, so 0, 0. And put 1 in, 1 squared is going to give us 1. So notice just so far what's happening is notice this function started going down. And it got to the lowest point, and then it started turning back around. So something I want you to notice, that's something that's happening to the function. So if I plug 2 in, I'm going to get 4. 2 squared is 4. So go to 2, 4. And I could keep going. So like if I plug 3 in, and then negative 3. And so the function is literally going to keep going. Okay, that's literally what's going to happen. It doesn't just stop, it keeps going. So like literally if you plug in 3 or 2.5 or 9, or it literally keeps going. Whatever you substitute in, you square it, and then you're going to get a y value, and you can keep graphing it. So a couple things I want you to notice. So first of all, this is the lowest point. That is called, it's called several things. It's called the minimum, because it's the lowest point. Minimum is like the lowest point of the parabola. Again, this is called a parabola, and so that's called the minimum. It's also called, that little point right there, the very center of that parabola is called the vertex. That's something I want you to notice. That is a definition. Those are both definitions that you need to be aware of. And then earlier we talked about, decreasing. So notice if I start plugging in, -3, -4, -5. So if I start plugging those numbers in, notice it's decreased. Again, I'm reading left to right. So this function is decreasing. It's getting lower. It's getting lower. It's getting lower. And then all of it, so it's decreasing from here to here all the way until it gets to the vertex. And then after that, it starts to increase. So again, we have a decreasing function, and then we have an increasing function. So that's something you need to pay attention to. Also, with the parabola, you're going to get to, I'm going to ask you a certain question. The point where it crosses the X line is very important. We'll talk about that meaning over and over and over in the future lessons. But right here, it hits the X line right at the origin, 0, 0. So later on, you're going to get to parabolas that may look like this. And see, I may ask you, where does it cross at? Those 2 points where it crosses the X line are very essential to knowing something. So these things right here, where it hits the X line, they're called 2 things. They're called x-intercepts, because it intercepts the X line. So they're called x-intercepts. So that's an x-intercept. This is an x-intercept. They're also called zeros. And again, we'll talk about why they're called zeros later on. Well, it's kind of obvious. Let me just tell you, this is -8, 0. And the point is -8, 0. This is 0, 0. So when the y is 0, that's why they're called zeros. So, the points where it crosses the X line are called zeros. So that's something you need to know. So far we talked about the minimum, we talked about the vertex, we talked about x-intercept, we talked about zeros, we talked about decreasing functions, we talked about increasing functions. So that's just the parts of a parabola that I want you to be aware of. So let's talk about the parent function. So I also wanted to talk about the parabola. Notice it's opening up at this point. You're going to get to, you might have a parabola that looks like this, and they're opening up. But you're also going to get to parabolas where they open down. And again, that's something that I want you to be aware of. It has a vertex. The vertex is the center of the parabola. The very center is called the vertex. Remember, the points where they cross the X line are called zeros or x-intercepts. Something I want you to pay attention to. But the other thing I want you to notice, on the parabolas that open up, the number out front of this x squared, so f of x equals x squared. Notice the number out front, which is a +1. If it's a positive number, then the parabola will open up. Now, if it happens to be a negative number, like f of x equals -2x squared, if it's a negative, then the parabola will open down. So again, pay attention to that, because how do you know if the parabola opens up? Well, if the first coefficient is positive, it opens up. If the first coefficient is negative, it opens down. Now, the last thing I want you to notice about a parabola is the very center of it is it's called the vertex, and we already talked about it in a previous lesson. We talked about the middle of this parabola is literally called, like we talked about asymptotes, and the asymptote is something where it goes, it's like an invisible line. Well, something similar to this, the very middle of this parabola. So let me use red here. So the middle of this parabola, notice it goes through the vertex. The vertex is literally the center of it, and this middle line is called the axis of symmetry. And in elementary school, or even maybe 6th grade, 7th grade, you call it a line of symmetry. So you might have like a triangle, and then you have a line of symmetry. What symmetry means is it literally cuts the shape in half. If I took a piece of paper and I folded it in half, it literally crosses with the other point. So in other words, if I folded this triangle over, this point would match up with this point. I literally would fold the triangle over, much like a circle. It has an axis of symmetry. If I folded this over, it would match up with that point. Or if I folded it, you could fold a circle in many different directions, but if I folded it, like this is called the line of symmetry or the axis of symmetry, it literally cuts the shape in half. Well, the same thing with a parabola, like literally when I draw this axis of symmetry, this point, if I fold it over, would match up with that point. So back to my original parabola. If I draw the axis of symmetry, and remember the axis of symmetry goes right through the vertex. So wherever the vertex is, that's where the axis of symmetry is. And so literally you can fold it over and it literally reflects. This is called the axis of symmetry or the line of symmetry. And like I often abbreviate this AOS, axis of symmetry. And so literally this point right here, notice it's one space away from the line of symmetry, and so you flip it over so it matches with that point. Notice this point is two spaces away from the line of symmetry, so if you flip it over, it will match up with that point. And so every point literally gets flipped over on the other side, and you can literally see it once you find the vertex, then you know the axis of symmetry is in the middle, and then you can literally flip it over and reflect it on the other side. Now let's talk about the parent function real quick. The parent function, if I had another function, for instance, if I had, let's work about y equals 2x squared. If I made a chart, an xy chart like that, you'll see that something is going to happen. So like literally you're going to get, let me do a quick chart. So if I did 0, 0, I'm going to get right there, I'm going to get 0, 0. If I plug 1 in, I'm going to end up getting 2. So plug 1 in, I'm going to get 2. If I plug 2 in, I'm going to get 8. 2, 8, right there. And then if I plug negative 1 in, I'm going to get 2. Actually, we can reflect it. Matter of fact, we don't have to even do the other side. We can reflect it. So it's one space away. This is two spaces away. We can literally reflect it and be able to do that. So this function, the purple one, looks like this. So notice if I had 2x squared, notice the parent function is x squared. So 2 actually makes it thinner. Or if I had 3x squared, it would make it even thinner. Or 4x squared, it would even make it thinner. Well, just the opposite. What if I had, let me use a yellow. So if I had y equals 1/2 x squared, and I made an xy chart from that, I'm going to end up with a wider, like a wider parabola to be able to do that. So again, the xy chart for the yellow, like if I plugged in -4, I would get 8. If I plugged in -2, I would get 2. If I plugged in 0, I'm going to get 0. So 0, 0 is here. -2, 2 is there. And -4, 8 is there. And remember the axis of symmetry right now is right in the middle, so I'm just going to reflect it. So 2 spaces over, 2 spaces over, 4 spaces over, 4 spaces over. So the yellow parabola is there. So notice 1/2 actually makes it wider. And so the same thing with the fractions like 1/2 or 1/3 or 1/10. It's possible if I had like 1/10 x squared, then it would even be wider out here, something like that. So, when you have a fraction, it makes it wider. Whenever you have a constant that's making it being multiplied, something bigger than 1, it's actually making it thinner. So it's all based on how it compares to the parent function. So I'm just going to simply ask you certain functions like how does this function compare to the parent function? It's wider. How does this function compare to the parent function? And it would be thinner. something that you need to notice based compared to the parent function.